I'll go ahead and start. Thank you very much for all for being here. My name is Marco Esters. I'm a postdoc in the Cortarolo group, and I will lead start our quick tutorial in our AFLOW functionality. AFLOW is an integrated infrastructure for computational materials discovery, and it was designed to automatically calculate materials properties and find new materials. This is our tutorial team today. This is me, Marco Esters. As you can see, we will also have 4 other presenters following up. One is David Hicks. He will talk a little bit about symmetry. He's also a postdoc in our group. Then there's Corey Osis, also a postdoc. You already saw Rico, also a postdoc in our group. And Cormac Tor is an assistant research professor in our group. He will finish up our tutorial. And if you were here earlier, you already heard Stefano Cortarolo. He is the head of our group and the director of the Center for Autonomous Materials Design. When we talk about finding new materials in a computational way, what are we particularly interested in? We're interested in novel materials applications that range from thermal barriers and coatings, for example, for energy and aerospace, which is what Stefano has talked about quite a lot. They need to have high heat resistance, and they should also be very resistant against corrosion. We're also interested in super hard and wear-resistant coatings, for example, as machine tools. As you can imagine, these machine tools need to be very, very hard and resist a lot of chemical and mechanical attacks that they face in their use. Another thing that we are interested in that we've worked on is biocompatible and corrosion-resistant alloys, which are very important for medical implants, for example, screws when you have broken bones. And photovoltaic materials, solar energy harvesting is always very interesting for energy applications. Lithium-ion batteries is another application for materials where computations can help. And superconductors and heat sinks for advanced electronics. In our current society, a lot of things are electronic, so having new electronic materials will always help technology to advance. So these are some applications that material science and computational material science can help. What's the challenge? The challenge is the enormous material space that we're facing. When we're looking at elements that we can actually really introduce or include in materials in materials, we're looking at, for example, everything on the periodic table except for the noble gases and radioactive materials. If we're just combining these elements together, we get a large number of elements. The binaries are about 3,000 combinations when we just take the 78 elements in the periodic table that we could use. And if we increase it to ternaries, we're already at 76,000 just element combinations. If we go higher and higher, we end up being the couple hundreds of millions of combinations just for different elements, not even talking about different structures. If we include different structures and different prototypes, which David will talk about later, we get to an almost unattainable number of 10 to the 177. That is pretty much impossible for an experimentalist to try, and also extremely difficult to achieve computationally. So where does AFLOW come into play? AFLOW comes into play using an automated materials discovery model where we take structures that we either take from an already existing experimental database, for example, the ICSD by the FIZ in Karlsruhe, or structural prototypes that we create ourselves, which is what David will talk about later. And then we do our quantum mechanical DFT calculations using our AFLOW package, and we mostly use VASP. Feed this into a database that can then be used to either feed it into machine learning models or do some other high throughput data analysis. And that is what AFLOW does, that is what we do. AFLOW is essentially a wrapper around DFT code that does a lot of post-processing and error correction. It's based on starting with an input file generation, that we then feed into a DFT code like VASP. We do our DFT calculations, check for errors, and use automated error corrections that we've developed over the years to see what kind of errors we get and how we can correct them. And afterwards, do post-processing and calculate, for example, electronic or thermal properties or elastic properties. And then we feed that into our database. AFLOW is open source. It's available under the GPL3. Here's a link to the source code that you can use to compile it on your system. We're not going to do that today because we only have 3 hours, so we mostly use our web functionalities, which are plenty. But it is something that you can do if you're interested afterwards. We also, AFLOW can be used on Linux and Mac and also on Windows. For Windows, you need additional software like the Windows subsystem for Linux, or Cygwin if you are on something in a system that's older than Windows 10, or if you already use Cygwin. And we have an installation script that you can use. It currently was tested for Linux flavors like Debian, Ubuntu, Arch, and Fedora. So there's an easy way for you to install AFLOW if you are not comfortable compiling from source, or if you just want an easy way to install AFLOW on your system. But it's available. Check out that website here, aflow.org/install AFLOW, to install it yourself if you're interested afterwards. For today, as I said, we're going to give you a brief overview. I will start after this introduction to AFLOW that you just heard, looking a little bit at our database and our search page, and also we'll show you how to access the database programmatically. We will talk about structure prototyping, which is what Dave is going to do. He will talk a little bit about our encyclopedia and how we generate different structure prototypes. Then we will switch to thermodynamic stability. Stefano was already talking about this earlier in his talk. Corey will talk about convex hulls and how to identify stable structures, and talk about synthesizability and how we applied this into the discovery of rare earth-free Heusler magnets. And we will essentially mostly talk about the convex hull web app here. Afterwards, Rico will continue with the thermodynamic stability of polar materials, which is notoriously difficult with density functional theory. And Stefano already mentioned the coordination corrected enthalpies method that we will use to correct the formation enthalpies of oxides. And Cormac will wrap it up with a little bit of machine learning using the PLMF representation for electronic and thermomechanical properties. And we have a web app for that too, which is what Cormac is going to introduce later on. If you're interested in learning more about AFLOW, as I said, we can really only scratch the surface of all that AFLOW can do. We have some past AFLOW schools. We're offering AFLOW schools, and we have some online. Schoolings can vary in length from half a day, which is this tutorial, for example, one that we recently held for the University of Maryland, to full-day workshops, to even 3-day workshops, which we held with UC, which is hosted by Texas A&M. And these multi-day workshops contain a lot of additional information, particularly on running first principle calculations using the AFLOW framework. So the part that I was talking about earlier, that entire workflow, we can cover over multiple days. So if you're interested in participating in or hosting a future multi-day workshop, please contact Stefano. Email address is here, stefano@duke.edu. And we can see if we can set something up if you're interested, especially in the command line functionality in installing AFLOW. I already mentioned that we have a large database of materials, and it is accessible through the aflow.org web portal. As you can see, we have more than 3 million entries with more than 500 million different properties. And we have a little bit of a breakdown of different properties that we have. We have, for example, more than 300,000 band structures. We have more than 100,000 charge calculations. We have 5,500 elastic properties and thermal property calculations. We have a lot of binary and ternary systems and entries. So there's a lot for you to choose from. And we'll start it off by going to the search page. We will show you how to search the database and find our entries. So this is going to be hands-on now. So if you all want to open or could open your browsers. See here. And go to aflow.org. And then scroll down to the Mendelib search. This is our search page. I hope it's not as slow for you as it is for me. My internet is not very fast right now. It's not done loading. My apologies. Can somebody from the AFLOW team write in the chat if they are having problems too, or if it's loading, or if it's just me? Okay, yeah, seems fine for David. Yeah, I don't know what's going on with my connection. It is really bad. So I can, while it's loading, hopefully will load, I can describe the interface a little bit. You see that there is a periodic table where you can choose your elements from to search. We have also different element selectors. For example, we have, you can just click on the metals and we'll hopefully, yes, thank you, Cormac. This is a backup link. It's probably not this is not the problem though. The problem is my internet. I can try if that one is maybe the backup link, aflowlib.duke.edu/search/UI search advanced. That one loaded faster. That's great. Thank you, Cormac. Yeah, now that I'm back, here you have your element selection. Let's search, for example, for silicon and carbon. You can limit the number of species, for example, to 2 if you're only interested in silicon and carbon in the compound. If you don't specify, it will search anything that contains silicon and carbon and potentially something else. So if we just want to look for silicon carbide, you just type in the number of species being 2. Here you have the different element selectors. For example, if you don't want to just have silicon and carbon, if you just want to look for alkaline earth metals or alkaline metals, you can click on those as well. And let's click the search button, see what we get. We see we get about 44 results with different structures here. For example, we have space group 186 for silicon 16, carbon 16. So they're different silicon carbide compounds with different structures. And let's, for example, filter for a property. Let's see the band gap. And for that, we have this little filter box here. There are different categories that you can choose from. I think the easiest way to look for a property is the band gap. Just type it here in the search bar and you will see a couple of different options. We want EGAP, the electronic band gap, just add it to the column and hit refresh or just search again. And you can see we have a lot of different options here, a lot of different band gaps. So you can sort by clicking on the columns. For example, here, silicon carbide in the space group 225 is a metal. And you can also, when you click on it again, sort it in descending order. The highest band gap is silicon carbide in the space group 186. So with that, I would like you to do a few exercises. I'll give you probably 5 minutes for those. And go back to the PowerPoint. Here. Use the advanced search functionality to find the band gap for silicon carbide in the zinc blende structure. The current search should help you find this easily. You can also restrict the search for just the space group 216. You can use the advanced search functionality to find the bulk moduli for materials containing titanium in the AFLOW database. And yeah, just check how many results are returned. And then you can restrict the value with the restrict value button, with the restrict value checkbox. Let me show you real quick where that one is. Here, you can restrict the value. For example, if I want to have insulators only, I can restrict it, and you can see that the metallic ones are completely gone. So you can use the restrict value button to see and then open an entry page of the material with the highest bulk modulus and see what the lattice type in the space group of the material is if you get that far. And as Cormac already said, there's an alternative AFLOW link if you have a weak connection. That server seems to be stronger. So I'll give you probably 5 minutes, and yeah, let's have 5 minutes for that, and I will talk to you then. If you have questions, please post it in the chat. Doesn't look like there are any questions. I think the 5 minutes are pretty much over, so I'll just demonstrate one of the exercises here, specifically number 2. So to find the bulk moduli for materials containing titanium in the AFLOW database. Let's go back to the search page. I mean, the first one is already almost answered. You see here the zinc blende structure space group number 216 is this one here. It's 1.37. You could make this even easier by adding the space group relax column and restrict the value to 216. That way you get, let me actually unrestrict this EGAP value. That way you get all these electronic band gaps for space group 216, and it's 1.37. The other prompt was to find the bulk modulus for all compounds that contain titanium in the database. And for that, let's just clear everything in the search page. So we want anything containing titanium. We do not want to restrict the number of species, because otherwise you would just get titanium if you set it to 1. But we would want everything containing titanium. And then we have the bulk modulus. We have multiple bulk moduli with different methods. The VRH method is kind of the standard, but anything would have been fine. And you can search. And you can see you get a lot of results back. Not all of them have a bulk modulus. That's because we didn't restrict the value. If you restrict it, just hit restrict value. If you refresh it, you see you get a lot less results back. And the one with the highest bulk modulus is titanium iridium. You can go click on this link here to get to the entry page to get a lot more information. And we can see what the lattice is, space group 221. When we go to the real space lattice, you will see that this is a cubic system, a simple cubic system with a Pearson symbol CP4. And unless there are any questions, I will move on. Are there any questions? Doesn't appear to be the case. Okay. So this is our search page. This is how you can look for our data, and that's all fine. But this really only helps you if you're doing a casual search. If you just want to quickly look for a compound that may suit your needs, this web page is great. It's easy to use. But if you want to look for data in bulk, When we enter silicon and carbon as elements, does it show only silicon carbide system, all materials with silicon and carbide in carbon? That is a very good question. The answer is it depends on what you put into the number of species. So I can show you the difference. Silicon and carbon, without restricting the number of species, gives you everything that contains silicon and carbon. You can see there's aluminum, carbon, silicon, and everything that contains silicon and carbon. If you just want silicon and carbon, let me get rid of this one. Yeah, here's even more after I lifted the restriction. If you want to have only silicon and carbon, you need to set the number of species to 2. If you're familiar with the ICSD search that we mentioned earlier, it works the same way. In most databases, when you look for them, work this way. You need to restrict the number of species, you need to set them to 2. Here you can see we have 44 results, all of them contain only silicon and carbon, but as soon as you remove that restriction here to set the number of species, you get a lot more back. Thank you for the question. Any other questions? You're welcome. Is it possible also to select binaries that have silicon and carbon only? Yes, this is the same thing. You just set the number of species to 2 and you have binaries that contain silicon and carbon only. If you want to have ternaries, for example, that contain silicon and carbon and something else, you just set the number of species to 3. Okay. Any more questions? Those are all good questions, all helpful questions. Okay. So as I said, this is all fine when you're looking for something real quick, if you just want to have do a quick search, but this is not particularly helpful if you want to do bulk data processing, for example, for machine learning or for any kind of data mining. So is there a way that we can access the database in a more programmatic way using, for example, Python or any other scripting language that you may like? And the answer to that is yes. For that, we developed AFLUX. AFLUX is a search language that is essentially mimicking our search page. So it's combining our search page along with all the properties that you may look for in our database and combine this into a search language with very, very limited operators. And this takes a little bit to get used to. We will practice this a little bit later, but bear with me a little bit when I explain the operators. We have a few operators in AFLUX that we need to use, but as you will see, there are not all that many, and we will learn more about them as we go. So it's basically a query as a URI. So you can enter, it's essentially just a link in your browser that you just query, that you can enter, and we will use the browser to essentially do that AFLUX search. And there's a few operators. I'll introduce them a little bit, and then I will explain exactly what they're doing with an example. So there's the usual block operator, so you can group certain things. We'll see a little bit what it does. We have an AND operator, which is the comma. A colon is an OR operator. The NOT operator. The loose operator can be used for different ranges or for wildcards. And there's a string operator and a mute operator. The mute operator, essentially, you can search for a property, but don't output it. For example, if you're looking for binaries, but you don't want all your search results to tell you that it is a binary, you can use that mute operator. And it's best to look at it through an example. This is a general AFLUX link. We have the service aflow.org/appy/aflux, and then there's the query. The query consists of a so-called matchbook and a so-called directive. The matchbook is basically the centerpiece, it's the heart of AFLUX. It is essentially what you have been doing, clicking on the search page and just entering what kind of properties you want, but this time in a more programmatic way. The example is whatever the server is, in this case, aflow.org, but also it also exists on aflowlib.duke.edu/search/UI. And here is the Matchbook. So this is the search clear. Let's go through it and try to understand what it does. Species is essentially tell you which species you want. So this one here says sodium, potassium. Colon is the OR operator, so this means that the species number 1 is sodium or potassium. Then comma, which is and, chlorine. So we're looking for either sodium chloride or potassium chloride. N species is the number of species, which is 2. So we are looking for sodium chloride or potassium chloride only, not sodium, chlorine, and something else. E gap is the band gap. We already saw that. And here we see what these loose operators mean. So 1 and 5 means that we want an electronic band gap between 1 electron volt and 5 electron volt. And at the end, we have energy per cell, which is the DFT energy. This is just an additional property that we want, but it's unrestricted. So if we open a browser and just paste and just write that link in there, aflow.org/appy/aflux, and then let me make sure both is visible. Height is here. Species, sodium or potassium, and chlorine. And species 2. I'm just writing down what this says in the slides. We're getting something back here. No, wait, what's going on here? Not AFLOW, AFLUX. It's querying the database. Can take a little bit because we have 3 million entries. So you can see it returns something here. This is a JSON in JSON format, in case somebody is familiar with it. The browser is just pre-printing it. Excuse me. And we can see, for example, we get a few additional entries. Here's the compound, it's potassium chloride. Then we have a so-called AUID. It's a unique identifier for our database, and an AURL, which is another identifier for our database. I'm just going to skip over it a little bit. We see the species, potassium and chlorine. Number of species is 2. That's what we restricted it to. And we have a band gap of 4.8 and an energy per cell of negative 6.7 electron volts. So if we want to use the not operator, for example, or the mute operator, we can go to n species and put the $sign in front of it. Let's put the $sign in front of species. Here's the, it will be the link to that. Can I increase the window size? Is that okay? Awesome, cool. Yes, and the link this here is for the muted property. Now let's see what happens to n species when we do that. Once it loads. You see n species is gone. And that can be very helpful because you get a LUX fail error message. I mean, this is the link that I used. I'm not sure. Can you try and load, just load again? Maybe that was a timeout. Because as you can see, it's working here. So this is what the mute operator does. If you want to, can I send the URI I used? I used this link here. This is what I used. just copy it and paste it into the chat. It should work. Does it work for me here? But as you can see, the mute operator just gets rid of the end species. If you restrict it to 2, if you know you already want to look for binaries, it can essentially make your output a little bit cleaner if you get rid of all the things that you're not particularly interested in, but you still want to filter for. So that's an example for the mute operator. Then there is, to go back to the slideshow a little bit, just to finish up all the other stuff. So the keyword list is available from the schema directive. So you just have question mark schema. I can also just show you what that does. Schema is a very long document. The schema square is something that you don't need to worry about too much. It's just a little bit of explanation, but here you can see all the keywords. Bravia lattice relax, for example, EGAP, we already saw EGAP fit. So you can browse through it, but I will give you in the exercises the properties that you need to look for. And at the end, we have formatting that takes JSON and HTML. You mostly want JSON as a directive with comma here. Then there's paging. Paging is the one that I want to quickly mention. By default, as you may have seen in your last query, you see that it gives you in this case 40 entries, but if you have more, it will by default only give you 64. The reason for that is if you, for example, have 300,000 entries that fit your query and you output everything into the browser, your browser is going to crash. For Python, for example, it's not that bad, but for a browser, this is important. The paging is helpful to just, if you have multiple entries, you can go through the different 64 bite-sized entries by using paging. For example, 1, 2, 3, or 4 for different pages. If you want everything, you just type in paging 0. In this case, it's not that bad because we only have 40-something entries. You can also use paging to sort for something. For example, if we want to sort by the band gap, first thing we want to do is we want to put the band gap to the front. And you can essentially sort in ascending or descending order by using paging 1 or paging -1. -1 is, you see that I don't misspeak here. It is all in ascending order unless you use negative values in your paging, but we can practice that in the exercises. These are the exercises. I'll give you maybe, it's running a little short on time because of my internet problems, but maybe let's try 5 more minutes so you can go through this a little bit more, especially maybe number 2. Might be in exercise number 2. Might be a very good one to start from what you have, and I will walk through one of the exercises later and then answer any questions that you may have. So the 5 minutes are about over. Let me go through the other exercise a little bit more. Let me actually make sure that we have a large enough font size. So I said that we want the materials, the space group numbers that contain the copper, titanium, but not vanadium. So we have the query, for example, first of all, species, and we want copper and titanium, so comma titanium, and not vanadium. The exclamation point is the not operator. And then we want space group relax. That's the query. And I'm having a typo here. Species is copper and titanium and not vanadium. And this is space group relax. As you can see, it's loading. This is the URI, and we see it has, for example, silver and copper. It has in titanium and silver, copper, and titanium. You will see a lot of compounds. What you won't see is vanadium in any of these compounds. So that would have been, here's the URI. That would have been the solution to that exercise. It takes a lot of practice to get the hang of AFLUX, but as soon as you play around it a little bit more and see what each command does, and reading through the schema a little bit, you will get the hang of it very soon. You can do the other exercises on your own time. And if there are no questions, I will hand the word over to David. But yeah, now's the time to ask questions. And apologize for the connection issues at the beginning. Okay, just waiting a few seconds for a question, but it doesn't look like there are any so far. I know it was very abstract. Does it automatically show all results with the API query? It shows all results only when you use paging 0. I will not show this in the browser because I don't know how many results are coming back. If you do this in using Python, if you just use curl or a Python way to query the database, this is a fairly safe thing to do. But if you paste it in the browser and you get a lot of entries back, your browser may crash. So yes, URL. If you do page 1, it will give you the first. Okay, so there are a few questions. If I do paging 100, will it give the first 100 results? No, it will give you the page. It will give you page 100. Each page is 64 entries, so page 100 will give you entries 64,000, 6,400 to 6,464. Retrieve the data from the website as well. This is a way to retrieve the data from the website. You can get the data from the search page too. You can get the data from the search page too, of course, but that is a lot of work to do by hand. This is a way to do it in a programmatic fashion. So, for example, using Python, URL request get method is one of these ways. Yeah. Okay. I will answer more questions in the chat. I would like to hand over to David, so he has enough time. And yeah, David, you're on.